In this last video of the course, you're ready to learn about the distribution of random walks. Let's go back to the initial problem. For 100 times you throw a dice. Depending on the result, you go some steps up or some steps down. This is called a random walk, and you know how to simulate this. But you still have to answer the main question: what is the chance that you reach 60 steps high? I'll give you a hint. Each random walk will end up on a different step. If you simulate this walk thousands of times, you will get thousands of final steps. This is actually a distribution of final steps. And once you know the distribution, you can start calculating chances. Let's go back to the example of the total number of tails after 10 coin tosses. The number of tails starts at 0, and for 10 times we calculate a random number which is either 0 or 1. We then update the number of times tails has been thrown by appending it to the list. To find the distribution of this walk, we start by setting a random seed, and then create an empty list named final tails. This list will contain the number of tails you end up with if you play this game of tossing a coin 10 times over and over again. Let's write a for loop that runs 100 times. Inside this for loop, we put the code from before that gradually builds up the tails list. After simulating the single game, we append the last number, so the number of tails after tossing 10 times, to the final tails list. Notice that the indentation here specifies that this last line is part of the top level for loop. If you now put a last line in here to print final tails, outside of the for loops, and run the script, you see that the final tails contains numbers between 0 and 10. Each number is a number of tails that were thrown in a game of 10 tosses. All these values actually represent a distribution that we can visualize. Visualizing a distribution. That calls for a histogram. On the top of the script, we add a line to import pyplot. And then, instead of the print statement, we call the hist function and specify that we want 10 bins. Of course, to actually display the plot, we need plt.show. If we run the script, the resulting histogram already gives an idea, but it's not very smooth yet. Let's head back to the code and now simulate the coin toss game 1000 times by changing the range in the top level for loop. This time, the histogram already looks better. If we change the code to do 10,000 calculations and run the script once more, the distribution starts to converge to a bell shape. In fact, it starts to look like a theoretical distribution. That means the distribution that you would find by doing analytical pen and paper calculations. Ideally, you want to carry out the experiment zillions of times to get a distribution that is exactly the same as a theoretical distribution. This will take too much computer time though, but 10,000 already gives a pretty good estimate. From this curve, we can see that in around 2,500 games of the 10,000 games played, you end up with 5 times tails. This makes sense, because you're tossing 10 times, and the chance of throwing tails is 50%, right? In the last exercise of this chapter, you will use a similar technique to simulate the dice rolling game in the Empire State Building over and over again. Go out there and win this thing.